Hello, it's Ryan. Today we're going to be starting our discussion on work, energy, and something I like to call POCO. To start this out, we need to go over all the definitions that we'll be using and probably and briefly go over what each type of energy is. So we'll start with some definitions. The first definition is energy. Have you ever tried to define energy before? Energy is the ability or capacity to do work. The ability or capacity to do work. That's how we define energy in physics. What do you think our second definition has to be then? That's right, we have to define work. So there are different definitions for work. I'm going to give you the definition I like. So we'll say if a force causes a body to displace, if a force causes a body to displace, that force has done work on the body. We could say that force is said to do work, but that force has done work on the body. And then the last thing we need to note under work is that whenever work is done, energy is transformed. So it's kind of a different statement, but it still goes along in the definition. Whenever work is done, energy is transformed. So those are our key definitions for this information, I guess. May feel a little bit strange, but by the time we're through with this, it'll all kind of make sense. And I want to note that in general, forces that do work are broken into two categories. We'll say are categorized in two major sections, we can say. I don't like that, but whatever. So number one, the type of forces. The two types of forces are conservative and non-conservative forces. And non-conservative forces. Conservative forces, we'll say that when work is done, the work is path independent. So if a conservative force does work, the work is path independent. So we could say when work is done, the work is path independent. And then the opposite will be true for non-conservative forces. We can just shorten our definition a little. Work is path dependent. And so I'll just briefly explain what that means. If you were to drag a crate, or drag anything along the ground, let's say, if you were to drag anything along the ground, so we'll make it our crate because we often do that. This could be one of us pulling a crate with a rope. Totally likely scenario for your everyday life. And so here's a person pulling a crate. And if that person decides to just pull the crate straight, like so, a certain amount of work it will take a certain amount of work, a certain amount of force to do that. But imagine if instead the person decided to zigzag to get to that same destination. Then the force that's opposing the motion, the friction force that you're kind of fighting against, that would act on the crate for a longer distance, and so it will end up taking more work to get the crate to the same position. So friction is an example of a non-conservative force because it's path dependent. Can you think of an example of a conservative force? Gravitational force is what I'm hoping you thought of. So we have a couple examples for you. Okay, well, there you have it. Our next set of definitions, we'll get the heading 5 fundamental types of energy. The 5 fundamental types of energy. And the 5 fundamental types of energy, they're called fundamental because any other form of energy is probably just some combination of one of or multiple of these. So this is fundamentally what all energy should break down into, at least for now in physics. So the first is potential energy. Potential energy. One way you can think of potential energy is that anytime a body has the potential to move, then we would say it has potential energy. My definition for potential energy will be energy associated with position. Energy associated with position. And what I'm going to do is I'm going to give you all 5 types of energy, and we'll give you a brief definition of each. And then I'll go into a more detailed mathematical explanation about a few of these types of energy that we'll be working with this semester. So bear with me, and by the end of everything, we should have a complete picture. The next form of energy is kinetic energy. If you recall from previous discussions, kinetic is always associated with motion, and that's what kinetic energy is associated with. So it's energy associated with motion. Anytime something has motion, it has kinetic energy. We'll learn later in the semester there are 2 kind of types of kinetic energy for us, rotational and translational, but for now we'll just be working with one, and you'll see later what that is. The third fundamental type of energy is thermal energy. Thermal energy. So oftentimes people will say thermal energy is heat energy, and that's a little bit misleading. My definition might not be any less misleading, but it's perhaps a little more elegant. So thermal energy is defined as energy associated with the random motions of particles. And then I want to note that really what we're talking about, of course, is temperature. Four is electromagnetic energy. What's another word for electromagnetic? It starts with L and is 5 letters long. Another way you could say electromagnetic is light. Light energy. Energy associated with light. And really, it's energy associated with electromagnetic waves, but that's just the science word for light. 5, the last of our fundamental energies, nuclear energy. Not nuclear energy, nuclear energy. And nuclear energy is energy associated with the nuclei of atoms. And that's the sort of energy we harness when we create nuclear power plants. So these are the 5 forms of energy, and we'll be discussing all of them by the time we get through Physics 2. But for this semester, and most of this semester, we'll be using just these first 2. And finally, near the end, we'll add in thermal energy. So this is Physics 1, and this is Physics 2, with a high emphasis on this. We're going to continue on. Because we'll only be using the first 3 energies, we're going to define really only the first 2 for you today. The first we'll talk about is potential energy. Potential energy, and potential energy has a few different flavors. We're going to use 2 of those. The first, and the one we use the most, is gravitational potential energy. And because we use this so often, I'll just abbreviate this with a PE. We'll use this the most, and so I'm going to just write PE, potential energy, for that. For the purpose of defining this stuff, I'm going to actually write PE sub G, just because of the next definition we're going to get. But the potential energy, due to any gravitational field that you're in, is always equal to mgh. And we'll define these where m, of course, is mass, g is the constant associated with the acceleration due to gravity. The constant associated with the acceleration due to gravity, so I abbreviated that. You may want to write it out. G is equal to a positive. I'm going to write a plus in front of it just to really push that. Positive 9.81 meters per second squared at the surface of the Earth, so that's what we're using. And h is, of course, the height above the surface of the Earth. So that's how we'll work with gravitational potential energy mathematically. I think it's worth making just a little note here that, no, let's save that. I don't want to make this confusing. Okay, the other form of potential energy is elastic potential energy. Elastic potential energy, that's given by PE with a little e after it for elastic, and that's always equal to 1/2 k x squared, and we'll say that where k is the spring constant, x is the stretch, x sub o, which we'll see in a minute, is the unstretched length or equilibrium length. Oh, let's make it L sub o, so it's different, sorry. And so x equals L minus L sub o. So this is elastic potential energy. If you can imagine a slingshot, there's a slingshot, and there's its rubber band with its little basket at the end to put your pebbles or whatever. Right now it's unstretched, it's just hanging loose. But if you were to take that slingshot and pull it taut back. So this might be L sub O. This would be L. There's a little pebble. Now this has elastic potential energy. Imagine having to hold this. You would be able to feel the rubber band in the slingshot pulling back on you. And so if you were to let it go, the pebble in the slingshot would have the potential for motion. And so you'll be able to feel and also see that this has potential energy. And as soon as you let it go, that potential energy would end up being transformed into kinetic energy. But we'll talk about that later. So that's elastic potential energy. And we'll use this anytime we ask you questions about springs or rubber bands or something that is elastic. Okay. Next we have kinetic energy. Kinetic energy. Kinetic energy is energy associated with motion, and we will use 1/2 mv squared. And I'll just define that v as the velocity. Actually, let's give one better. V is usually velocity, but we're going to write that it's speed. And that's a very important change because notice the square. If we put a positive or negative in for the velocity, as we square it, we'll only get a positive value out. And so it takes me on to the next point that I want to make about energy, and that's that energy is a scalar quantity. Energy are scalar quantities. And so direction is not accounted for and doesn't really make sense to use. The units for energy, named after a man, I think James Joule, but the unit for energy is 1 kilogram meter squared per second squared, which is 1 Newton times meter, which is 1 joule. And so we say that, or write that like this, joule. So a little notes on energy. Our last definition is for work. Work, remember, anytime a force causes a body to displace, that force does work on the body. And anytime work is done, energy is transformed. Work is defined as the force multiplied, or the parallel component of the force multiplied by the displacement. So this is my favorite definition for work. It's the parallel component of the force times the displacement. The mathematical definition is a dot product, F dot S. This is a dot product, often referred to as a scalar product, because it always gives a scalar, not a vector. We take two vectors, multiply them together in this special way, and we get a scalar out. Any dot product can always be represented this way. The magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. So work can be represented this way, and this is probably the easiest way to think about it for our class. Actually, I think this is the best and easiest way to think about it, but we'll see in examples, and you can choose however you'd like. So we'll just note that phi is defined as the angle between F and S, which is, of course, the displacement. I'm going to show you a diagram for this one. So we're going to do work diagrammatically. So in this picture, I'm just going to represent a displacement like this, some displacement vector. And I'll also represent or show a force like this. This could be some force acting on a body where this S is the displacement the body takes. And the angle between these two vectors is what I've called phi above. And so this would show yield that the work is Fs cos phi, like we said. Another name for dot products is a projection. And so when we say we want to take F dotted with S, what we're really asking is how much of this force vector is in the direction of this displacement vector. And so if you imagine shining a light from above, then this vector and this displacement vector were real things somehow, then this force vector would cast a shadow on this displacement vector, and for whatever reason that shadow will be red today. And so if you can imagine that shadow cast by the force vector on the displacement vector, that is the projection of F on S. And so it really is the product of this projection, F parallel to the displacement, F parallel to the displacement, times the displacement that would yield your work. So that's something I always like to talk about briefly when I introduce the mathematical definition of work and dot products. So that's kind of a long introductory video to some of the language. The next videos will be examples working with work, energy, and the mysterious POCO that I haven't defined for you yet.